the session. Today's topic, as announced, enhance our recovery and how our L-Vis can help doing that. We will try to go through just like a brief description of the unit and the working principle, how we mechanically and electrically can integrate this into the system. Maybe some a little bit more about the enhanced oil recovery application and in which segment of this application L-Vis can fit in. Some lab tests which we done in the past, and additionally some field tests which we done. Maybe a short ROI with some examples based on data from the Canadian Pelican Lake. Some projects from the past that you have an overview that it's not something we do for the first time. Maybe a summary, and then if we have time for short Q&A at the end, I assume we will not take all the 60 minutes just for the presentation. If you have really, I don't mind answering any questions in between. So just unmute yourself. Put the question to the audience. I will try to find the answer. Otherwise, free to collect all the comments and the questions for the discussion. And we can then begin afterwards. So on the picture, actually, you see two models of the L-Vis. The button model is actually the L-Vis 510, having this part here, which is out of the line, and this part with the measuring head is actually in the line. On the top end of the picture, this is the L-Vis 520X. It's a unit designed for mainly X environments in petrochem applications where you need like class 1 different classification or ATEX certification. Both can do the same thing, use the same measuring principle. Just due to the hazardous conditions, the design is a little bit different due to in the mechanical range, the housing, and how we deal with the interface between the process and the outside world. So what the L-Vis will do, actually, it really measures dynamic viscosity at a single shear rate. For those of you who are not familiar with the words dynamic, kinematic, etc., the dynamic viscosity is the pure viscosity from the partial model. If you may be familiar with viscometers, where you have like capillary type, where you measure time, for example, to this is typically a reference viscometer in some labs. And this time depends, it tells you about the viscosity. This is actually the kinematic because the density is involved. The typical pure viscosity value is dynamic viscosity, which is determined at a single shear rate, meaning that we can control the rotation speed of the bob and somehow mimic a lab configuration of a DIN type. And process, yes.
Excuse me, Dr. Miha, I'm not sure if you have switched after the first slide, but the presentation shows the very first slide and not full screen.
I've switched to the next slide. I'm not sure why not. Just move on. I'll try to do something else.
All right.
So this is, do you see this? First slide, second slide, third slide.
Yeah, but not in full screen. But now, yeah, we see.
Yes, I will try to do it. I have switched to full screen, but I have not seen it, so I'll try to leave it like this.
All right, all right.
So I hope you see it now.
Yeah, we see it now.
So what we have here is, so the L-Vis will measure dynamic viscosity and process temperature. And using these two parameters, we can then calculate additional parameters if necessary. A typical one would be to have a temperature compensated viscosity at the mainly meaning you measure at 35 and you would like to calculate this to a lab value at 20, for example. There are two options here. One is the Arrhenius function and one is the ASTM D341, which is mainly intended for Newtonian samples in the petrochem industry. And we can also calculate kinematic viscosity by using a fixed density value, a single density value, which you type into the unit, and the unit will then do the division and calculate the kinematic viscosity. Just a briefly description of the measuring principle, how actually we determine the viscosity. You see here the configuration looking from the top into the measuring chamber. It's very similar to a DIN cup based rheometer where you have a cup and a rotating cylinder inside. However, in order to facilitate sample exchange, we've opened this cup a little bit, and also the concentricity or the gap between the bob and the cup, it's not fixed, but it's gradually decreasing. So when the sample is sucked in due to the rotation of the bob, it's somehow squeezed through the gap, and this squeezing causes this part here to deflect. It's a little bit flexible, and this deflection is actually correlated with the viscosity. The higher viscosity at the same rotation speed, the higher the deflection. In a 2D representation of the gap, we have this first part which is parallel. This is actually somewhere in the beginning, and then we have a decreasing. So sample goes in, it's squeezed through. This part deflects. We measure actually this deflection, or measure the distance of the deflection, and then correlate this internally in the model into the measured viscosity, and the model is determined using standard oils in the factory before we deliver the unit. From the head point of view, so this part is actually in the liquid. You would have here this on the top. It's called deflection sensor and temperature sensor. So this part here is fixed, and this deflector is like a metal deflector, will move away from this fixed part, and this distance will be measured, and the distance is correlated or linear to the viscosity measured. This is the bob. We can also exchange bobs in let's say different diameters according to the configuration necessary for particular applications, depending on the viscosity ranges which you have to cover. Then you have this rigid part of the sensing head. This is actually to protect the system, so the flow will always hit. If this is installed in a pipe, the flow will always hit this rigid part, and then this very thin end of the open cup is actually the flexible part, which will deflect due to the viscosity in the gap, and the bob is rotating at a speed which is controlled by the electronics and the motor control in the unit. The integration, so we have to somehow integrate this into a tank pipe and also into your PLC. There are different possibilities possible. We do provide different pipe adapters according to the diameter of your pipe that you have. You also have welding adapters if the pipe is 4-inch and wider. This is possible. And we also have some so-called bypass adapters for very thin or small lines, where you either weld your line to these nipples or you screw it in, because there are options with threads or without a thread, or so that both options are available. Different flanges. For our standard flange, which is the so-called L-Vis Anton Paar flange, we also have the variant possibilities, mainly for the food areas in food applications, and also some DIN and ANSI flanges if it's required. We typically don't recommend to use them, because with DIN and ANSI flanges we create a dead space due to the TPs of the DIN and ANSI. A typical recommendation for your type of industry would be to use the Anton Paar flange and some kind of an Anton Paar pipe or welding adapter together with this flange. On the other end, you have to somehow, now the unit is inside, we rotate, we get measured values. Those are controlled and converted inside the unit. It's a so-called smart sensor with different boards inside. The main boards will recalculate, measure everything, provide the value, and this value is then either shown on the screen itself of the device, it could be then also transferred to a PLC using, let's say, standard field bus communication boards or analog interface 4 to 20 milliamp. It's only one board per time, so either one of those. Alternatively, you can connect the unit to the MPDS5, which is an Anton Paar evaluation unit. This could be up to 250 meters away from the sensor. And then from the MPDS5, which is built into a, let's say, switch cabinet somewhere nearby the unit, additional connection to the PLC. Why we would do something like this? The MPDS5 is just a little bit more convenient interface. It's a touch interface, it's a larger screen. Plus, we have the possibility to connect this unit to a so-called L-Vis software for data acquisition and visualization, data recording, follow-up processing, statistics, and so on. And we could actually attach to the MPDS5 also a density sensor, for example, to calculate kinematic viscosity or just to show a density value of the liquid itself as well, if this would be required, or any additional sensors. So the MPDS5 in general is able to take in any 4 to 20 milliamp capable sensors. So you could actually attach, maybe if you need pH, conductivity, or something else as well. And then send these combined to a PLC or combined to the L-Vis data acquisition software if required. Just an installation example. This is actually a trial for polymer flooding fluid in the Netherlands, where the L-Vis has been installed in the recirculation line of the so-called mother fluid tank using this bypass adapter. In this case, it's installed vertical into the adapter. If the line would be, or the diameter of the line would be larger, we would typically then use some kind of an adapter or a welding flange. I assume you are familiar with the application. Just maybe like a brief overview so that we have they use the same terms, or at least get familiar with the terms I will be using. Typically, you have a production well where oil and water and whatever you push in the injection wells are collected, and then the oil is separated. The water itself and polymers are maybe also separated and reused in the next cycle. What you try to do is you have multiple injection wells, and let's say not single, but less amount of production wells, and with the additional means that you modify actually the water properties, you try to enhance the push out of the oil in the ground in general. Where we fit in, so what we do is improve mobility of water by increasing the viscosity and try to make the properties of this fluid, which is used to push the oil as close as the target oil. Where we can't fit in, I mean, the enhanced oil recovery has multiple sections, from gas to foam to chemicals to thermal, etc. So where we fit in the areas where you use chemicals, typically polymers, to modify your brine water or water which you use for oil production, and increase the viscosity of the water which you push into the injection wells. There we fit in. So no thermal or gas or foam stuff. This is unfortunately not possible because it's just measurement of a polymer solution in water at the end of the day. A typical configuration of the installation will look similar to that. So you have some kind of recovered water which you use in a water pump. You maybe filter that in addition. And then you have this typically polymer is provided in a powder form, is then mixed with water in a so-called curing tank to cure for a particular time so that the polymer can react with the water. Is typically also stirred. This would be the first point where the L-Vis could be installed to monitor the curing tank viscosity. Then this is again filtered, fine filtered, etc., and gets to the so-called mother liquor storage tank, where there would be the second point where we could measure the viscosity of the polymer fluid. And after that, it's typically mixed again with recovered water to the final concentration, and a very high pressure is used then to pump this into the ground. Unfortunately, on the last step, so immediately before the injection well, we can't measure because the pressure is just above the L-Vis pressure limits in that case. So we had similar examples, or we tried some cases at the field nearby Vienna with a very similar configuration like this. However, also there, it was not possible to use it for the injection well just because of the pressure ratings. Some comparisons with lab, and this is been done with a polymer from SNF. SNF, according to my information, is one of the largest producers or providers for polymers used in the enhanced oil recovery industry, and polymers for other segments, also in the oil and gas industry. What we have done here is we've prepared different concentrations of the polymer, starting with 500 ppm up to 15,000 ppm. Then performed a lab measurement of the viscosity. This is being done with the RealLab QC. RealLab QC is a lab viscometer from Anton Paar using a DIN cup geometry and adjustable shear rates. And we've done the same using the same sample at the same temperature, then again with the L-Vis, just in the lab conditions. And we have run the L-Vis at 50 reciproseconds. That's the shear rate for the measurement. And we use the same shear rate settings for the RealLab QC as well. And all those points here, and then the line in between is actually the correlation between lab and process in that case. So in a sense, it's a perfect line if we deal with the lab, where we have like very, very stable conditions, very stable temperatures. So one can achieve a perfect correlation. In this case, this Y is something like X could be actually used if you would have some other lab data somehow to convert the L-Vis viscosity in some kind of a lab type viscosity just by using this, we call this gain and offset values. I forgot to mention in the beginning, the gain and offset values are possible for the unit, so we are able to manipulate, or let's say adjust in a way the values the L-Vis is showing by using manipulation values or so-called offset and gains. Standard or default values is gain is 1 and offset is 0, and this can be then converted or reset in the field if required. This is some additional lab data where we've run a very similar experiment. However, we've tried to use different shear rates. So the L-Vis, so you see this, the whole line of the red dots and the blue dots. These are just two different concentrations, and the whole line is actually a rheometer measurement. So we've done a whole sweep of shear rates between 10 and this is 200, like 500, 5 to 600 reciproseconds. And then we have done the same. I mean, the same is not possible with L-Vis because it's not like a pure rheometer, but we do have limited options of modifying the shear rate at which we measure. In general, the L-Vis has two types of gearing available, 1 to 5 and 1 to 25, which gives us a rough change in the shear rates at which we measure. And then at the end, we can also manipulate the rotation speed of the bob using the firmware of the device itself. And currently 3 defined speeds are always possible for every device. And in this case, we use this option and measured at 3 different shear rates of the L-Vis itself, just to show that the correlation between the measurement of the lab, the rheometer, and those 3 points of the L-Vis correlate very nicely. In addition to the lab test, we've also collected some field test data. The first one shown here is a flow rate influence using the polyacrylamide samples, where in this case a customer has doing quite significant modifications in the flow rate and changed the velocities in the pipe up to 1.2 meters per second. And did tests with different concentrations of the polymer, and then collected the sensor values. Most of the time there are some outbreakers, but most of the time it's a very nice linear representation. And this dot, or this let's say cloud of values, is quite close together, because in this case you cannot control temperature completely perfect, and you will get these influences of the temperature. For those who are not that familiar with viscosity, 1 degree centigrade change of temperature will typically lead to a 10% change of the viscosity value for a general sample. And the details are always dependent on the sample itself, but it's quite a significant change of the value with regard to temperature. The second point, and we have here again a little bit of cloudiness in the values, mainly due to temperature effects, is that we have the polymer concentration and the viscosity just at a specific, this is N, at a specific flow rate. Again, a big dot here, a big dot here, a big dot here, a big dot here, a big dot here. So a very nice, in my opinion, correlation from a field trial with different polymer concentrations at very, I would say, rush conditions with regard to flow rate and temperature changes. Again, this is again from a field. What has been done here is again to have rheometer and L-Vis compared for different viscosity, and those different viscosities are just related to different concentrations. Where you see these red dots, this is the rheometer, and there's those red 4 angles at the top are L-Vis measurements. Then the overlapping at different shear rates again. So this is shear rate here, and this would be the viscosity. So there's, like, I would not say almost perfectly overlapping, but a very, very good overlap between what you can measure in the rheometer and what you can measure with the L-Vis. On the ROI side, this is some typical values which we have collected in the past. They may change today. I've not double checked if this is still true, but in total you have the cost of, let's say, injector producer wells, then you have the polymer water facility, the polymer itself, and some kind of a maintenance. This is from the Canadian Natural company in Canada, which operates a lot of let's say injection wells in the Pelican Lake field. If you do then the comparison, I've done this, or we've done this for comparing the Pelican Lake with the King field. This is in China, and they have quite a significant amount of wells, using then the daily production, then counting in the value of the oil, the polymer cost, etc. You can find out that the payback or the return on invest for a specific unit is very, very fast. I will not say that it's like in days and months. I mean, it's here, it's written here, but definitely less than a year, according to the oil price at that time. So definitely makes sense in order to save on polymers, which are the main cost on a daily operation. Some projects from the past. We've done different evaluation projects and then also in-field tests. However, we don't get any further information once the units are installed. This is just some kind of a black box, partially because not all companies share the data afterwards. Different projects with Shell International, Shell in Canada, the oil fields of OMV in Austria nearby Vienna, with Total in France, Carn Energy India, and some multiple projects with BASF and YPF throughout an engineering company in South Africa. So in summary, what L-Vis can do, it can measure very accurately and comparable with the rheometer the viscosity of the injected polymer solution at a low pressure site of the arrangement, either in the mother liquid or in the mixing tank. It will provide you real data analysis at multiple shear rates if required. The measurement frequency currently is like 25 seconds. So every 25 seconds, you will get a new value, which is then either shown on the screen or transferred to a PLC. And actually, the main goal is either, first of all, to have the right concentration, which you need, and second, to be on the target concentration to save on polymer costs. This would be all from my side for this part, but I would open up the discussion here. I will stop the sharing and reshare again if you need a picture, and would appreciate any comments or questions from your side.
Thank you, Dr. Miha. Please, if you have any question, you can ask, raise your hand, or type in the chat box. We are not yet finished. We will go for the live demo and Dr. Ahmed Nouh later after that. So if you have any question, please ask now. If not, we can continue. Mr. Yusri, can you please unmute your microphone and talk?
Yes, hello everybody. I'm just asking if there's any other products dealing with the high pressure well or another enhanced air recovery like steam, like CO2, etc. Thank you.
No, as I said, this was like slide 3 or 4, at least from the viscosity point of view, L-Vis will not deal with the high pressure site, and not with steam and not with similar products. The only product which we have in our portfolio would be a densitometer, which is suitable for pressures up to 125 bars. And this would be actually the high end on the pressure side, but this is not viscosity, this is density. And density, again, limited to liquids. Very difficult to deal with steam because it's like a mixed sample and gases as well. So again, it would have to be some kind of a polymer solution based on water or similar.
Okay, Dr. Miha, thank you. I'm just have another question. What is the density of such polymers in general?
Actually, we have not measured, so I would have to guess. But I would say it's comparable to in a range of 1.3, 1.5. This would be my guess. Otherwise, I can double check if we have some data from the past, but we actually haven't measured the density when doing the tests. And it also depends on the concentration. So unfortunately, I cannot give you a number.
Okay, we've got it.
في أي سؤال تاني؟
أشكرك يا مستر محمد، شكرا.
Any other question please؟ عفوا أستاذ يسري، شكرا لك. Can you please all? I will, Dr. Miha. I will mute all, and then you can unmute yourself.
Just hold on. Where is this?
All right, now it's okay. So, Mr. Muhammad, can you please talk? Mr. Muhammad Samba.
Hello.
Hello.
Yes.
Thank you for this lecture. First, I would like to how to control the molecular weight for the polymer, and how the effect of the molecular weight to let the polymer to bypass through the pores, because sometimes we have a polymer, but the problem, this polymer cannot fit through the pores. How we can control the polymer through the molecular weight?
I mean, I'm not a chemical expert on polymers, but from the experience we have, the molecular weight is proportional to the viscosity. So this is something which is correlated. And what we know from the past and some tests with customers, they tweaked this to the viscosity value at the end. However, which viscosity is suitable for your well, this is something your research and analysis has to provide. This is not something we do or offer. We just offer means to control the liquid which you pump into the injection well by measuring density, viscosity, etc., and other parameters. But we don't provide an expert on analysis on where this target value should be or which polymer you have to use. This is something where the companies we have been working for the past have done at some point in time, selected a specific polymer and have already selected also particular concentrates of the polymer, sometimes even with experimenting by starting, let's say, nearby water and then moving gradually up, and then doing the analysis of the oil which was produced over a specific time. So this is some type of the let's say, analysis done before you go into the, let's say, production.
Okay, thank you for this explanation. The second question I want to ask, the title of this lecture is to inject low viscous fluid. What you have mentioned that our purpose is to low the mobility ratio. And if we wanted to get mobility ratio is very low, that we have to inject the fluid with the high viscosity. How we can match this? Do you mean that the injected fluid should be less as much as we can with the low viscous?
In general, the literature will tell that the viscosity of the injected fluid should be very nearby the viscosity of your sample in the ground, which you try to mobilize out to the production well. So it's about the analysis of what you have in the ground. Because as soon as you let's have a higher viscous surrounding in a sense and the very low viscous water which you push through, it can happen that channels build and you actually just pump water around and you don't reach to the site of this water channel. So by typically increasing the viscosity, you enhance the reach of the within the small channels in the ground which travel from your injection well to the production well, and then they will push in a sense more. However, what exactly you have to adjust, this is again the same question as before.
Mr. Muhammad Samba, is everything clear?
Yeah, yeah, everything is clear. Thank you for this
All right,
clarification.
you are
Thank you.
welcome. Dr. Muhammad Al Busifi,
Yes. Morning.
good morning. How are you?
Fine, thank you. Thank you for this fruitful lecture. I just have a question that since we are dealing with enhanced oil recovery, the oil we are handling will be a mixture of many unlimited things, such as beside the crude oil, we have water and we have emulsions. Also, the type of emulsion might be will be different. Also, there will be sands and so on. Will this device can handle all this type of mixtures? This, it will not get blocked or somehow,
Yes.
you know.
Maybe just I'll share again the presentation. I can then explain a little bit easier. So in general, we can handle any mixture. It's not a problem to handle an emulsion. So not just a polymer. We do measure emulsions. A typical emulsion would be maybe a cream or a shower gel. We measure also emulsion in cold asphalt, where you mix bitumen with chemicals and water with a high shear pump. It's a clear emulsion. So small bubbles of air in the sample will not somehow jeopardize the measuring principle. We are unsusceptible for this and can do any suspensions and emulsions in general. So that's not a problem to measure. The main problem with suspensions, in a sense that you would have particles of sand or remaining particles of sand which have not been filtered out, is that if this is really hard sand, if these are soft clay type of particles, that's not a problem because they get squeezed. And we do have installations, for example, in the ceramic industry, where we measure ceramic slips, which are used to produce sanitary ceramic type of stuff. However, if you have extremely hard particles, the main problem which we can have is in the range of which type of particles we can handle. So there's a limit in a sense that we don't block the unit. Like that here, for example, just try to draw that here we have like a particle. So if this is the particle which has the side of the gap, this could then block the whole measuring chamber. We do rotate in a way that we rotate first in one direction and then re-rotate in the backward direction just to have a relative measurement. So there is some self-cleaning effect of that built into the unit. However, if the concentration of those particles is very high, and they're really likely large, it could happen that they partially or temporarily block the unit, which will be then displayed on the unit itself as a current error. Why a current error? Because we try to the motor tries to draw current in order to rotate the bob, and this current goes up to a specific level which is limited, and then we send out an error message, in a sense, current error, meaning blocked bob or blocked rotation of the bob. So we can handle all the samples. However, we have to be careful on the particle size or on the sand particle diameter size, which we allow for the unit to handle.
Thank you for this clarification. So what's the stability, of the measurement fluctuating as because of the condition of the flow?
So from the flow conditions, as shown in one of the prior samples, we have not seen, let's say, maybe like plus minus, the typical would be plus minus 1% in very ultra stable conditions, and then maybe up to plus minus 2% if you have very unstable flow conditions. But generally, we are not dependent on the flow itself due to the installation and due to the construction of the unit.
Thank you very much.
All right. Any other question? Okay, so Dr. Miha, it seems there are no more questions.
If there are no more questions, then I would thank you very much, everybody, for taking the time out of your busy schedule to listen to this presentation and the discussion we have. If you have any further questions or requests, please reach out to Mohammed Fatih, and then he will pass this to the office in Graz. We appreciate any trials which you may have. We can arrange for tests if this would be required to support you throughout the enrollment, if you have any plans to do so. I would suggest that, Mohammed, that the group makes like a 10-15 minutes break before you start with your next session at 11 o'clock Central European time at least. Thank you very much, and bye-bye.
Thank you, Dr. Miha, for this informative presentation. We really liked the presentation and information in it. And please don't leave please, all participants, don't leave the lecture. We are not yet ended. Dr. Miha, thank you. So you can end the presentation. We will continue with another session from Egyptian Petroleum Research Institute after a 10 minutes break. Thank you.
Thank you all. Have a nice day. Bye-bye.
Bye-bye. شكرا لكم جميعا، ولكن يا ريت ما تسيبوش المحاضرة. احنا لسه معانا محاضرة تانية ان شاء الله كمان 10 دقايق استراحة. هيكون معانا دكتور احمد نوح من معهد بحوث البترول المصري، هيكلمنا عن الفورميشن دامج وقد ايه التوبيك ده ترندنج في مجال البتروليوم انجينيرنج. فان شاء الله هتكون محاضرة ممتعة، ويا ريت الكل بعد 10 دقايق نكون حاضرين مع بعض ان شاء الله.